Zart University. International Undergraduate Program. Department of Electrical Engineering. Electrical Engineering Project present. Autonomous in-house farming system. Agriculture has been the oldest human industry, and it's certainly no stranger to technological change. The challenges today are to ramp up the food production. The engineers and farmers of today are working together to create a technological solution. Precision agriculture, smart farm. Now, we're on the verge of witnessing another fundamental shift in agriculture. Thanks to a new industrial revolution and the technologies of Industry 4.0. Automation allows farmers or users to apply optimal amount of water and fertilizers upon requirement. In-house farming system is an outcome of a traditional agricultural techniques and living in an urban society. The future of such an in-house farming system depends on the judicious management of autonomous system. The goal is to enhance productivity of a product from plants without any adverse consequences, and maximize efficiency of available input resources. It's high time to exploit all the modern tools by bringing technology and agricultural science together for the improved urban life of busy people and researchers who want quality products from plants. Precision agriculture merges the new technologies born of the information age with modern agriculture. The key factors which keeps the new generations away from cultivation are no time for activities of continuous monitoring, watering, fertilizing from the hustling life and their full-time job, and above all the scarcity of skilled workers, and higher operating costs of agriculture.
Timeline. For first semester. Week 1 we start with gathering all the necessary information for our work. Week 2 we classify each relevant information for our work. Week 3 analyze the data that we have collected. Week 4 made an analytic report for the collected data to prepare for our project on the next semester. For second semester. This is the timeline for our second semester. Let's start with Week 1. Week 1 we plan work schedule that we have to do in this semester. Week 2 we created a system for our prototype model. Week 3 we designed a planting cabinet by using Shaper 3D. Week 4 after we finish designing the system and the cabinet, then we prepare the equipment to use with our prototype. Week 5 to Week 6 after having all necessary equipment for our prototype. This weeks we try to build our hardware at the laboratory. Week 7 to Week 8 we finished our prototype. This week we tried to set up the system that we already designed. Week 9 to Week 11 these weeks we tested the software and hardware. And we fixed all the remaining problem. Week 12 the last week, we created and summarized the results of the experiment.
System overview. The input materials or sensors send all the collected information to the PLC. The PLC then acts as central node which collect and process all the information according to the pre-processed program. The program consists of auto and manual mode which users can choose between each two or shift between each mode. Then, all the information will be displayed and controlled by using HMI. The objectives of our project are to develop in-house farming systems that are suitable for everyone. Second, to study and develop ecosystem of plant to use with in-house farming system. Lastly, to study and develop autonomous system to use with in-house farming system.
Related theories. What is PLC? A programmable logic controller, or PLC, is a ruggedized computer used for industrial automation. These controllers can automate a specific process, machine function, or even an entire production line. The PLC receives information from connected sensors or input devices, processes the data, and triggers outputs based on pre-programmed parameters. Depending on the inputs and outputs, a PLC can monitor and record runtime data such as machine productivity or operating temperature, automatically start and stop processes, generate alarms if a machine malfunctions, and more. Programmable logic controllers are a flexible and robust control solution, adaptable to almost any application. In this project we use Modicon M221, TM221E16R. The PLC that we used in this project is provided by Schneider Electric Thailand. What about HMI? Human Machine Interface, HMI, is a user interface or dashboard that connects a person to a machine, system, or device. While the term can technically be applied to any screen that allows a user to interact with a device, HMI is most commonly used in the context of an industrial process. HMI technology is used by almost all industrial organizations, as well as a wide range of other companies, to interact with their machines and optimize their industrial processes. HMIs communicate with programmable logic controllers, PLCs, and input/output sensors to display information for users to view. HMI screens can be used for a single function, like monitoring and tracking, or for performing more sophisticated operations, like switching machines off or increasing production speed, depending on how they're implemented. The HMI that we used in this project, the 7.5 inches ProFace GP4401T Series PFX GP4401TAD provided by Schneider Electric Thailand. Relation of light wavelength in plants. A crucial component in the growth of a plant besides water and oxygen, is sunlight. By receiving it, a plant can convert sunlight into edible food that it can use. This process is called photosynthesis. We know light behaves as a wave. As such, it displays different properties depending on its wavelength. For example, a source of light with a wavelength of around 650 nanometers will be detected as having a red color. Multiple studies have been conducted on how different colors of lights can have varying effects on the growth of a plant. The effects of each color of light. Violet enhances the color, taste, and aroma of plants. Blue increases the growth rate of plants. Green enhances chlorophyll production and is used as a pigment for proper plant viewing. Yellow plants exhibit less growth compared to blue and red light. And more. Methods.
Plant selection. For our plant selection, we have chosen 3 types of plants that are categorized according to their part of consumption. First one is Thai basil, second one is cherry tomato, and the last one is cayenne pepper. Let's start with Thai basil. Thai basil is the plant that we use their leaves for our consumption. It grows well at temperatures around 24 to 25 degrees Celsius and have moistness between 45 to 50%. This plant has trunk height between 70 to 80 centimeters. It has life cycle around 8 weeks. It can be planted all season. The other one is cherry tomatoes. Cherry tomatoes is the plant that we use their fruits for our consumption. And inside contains watery texture. It grows well at temperatures around 24 to 30 degrees Celsius and have moistness between 70 to 80%. This plant has trunk height between 40 to 50 centimeter. It has life cycle around 5 months. It can be planted in winter seasons. The last one is cayenne pepper. Cayenne pepper is the plant that we use fruits for our consumption, and inside is not watery texture. It grows well at temperatures around 20 to 30 degrees Celsius, and have moistness between 60 to 70%. This plant has trunk height between 50 to 60 centimeters. It has life cycle around 6 months. It can be planted all seasons long.
Materials selection. In this autonomous system, the selected materials can be separated into 2 types according to their behavior, which are the input materials and output materials. The input materials consist of pH sensor, water temperature sensor, air temperature and humid sensor, light intensity sensor, water level sensor, EC sensor. Next is the output materials, which can be controlled manually or by system autonomous feature. The output material consists of LED, ventilator, humidifier, water chiller, water pump, fertilizer pump, and lastly acidic pump. Next topic is system design. System design is separate to hardware design and software design.
Hardware design. For hardware design, there are 3 steps. First step, we research about smart in-house farming system created in this world. Second step, we created a prototype by using Shaper 3D, and the last step, we build a demo smart in-house farming cabinet at our laboratory. Let's start with first step. For this step we research about smart in-house farming products that are sold worldwide, following these 7 categories: price, system, application support, number of plants, materials, size, and connectivity. The first product is GetLeaf. This product has a price of $2,699 or 87,500 baht. It consists of 7 sensors and support iOS and Android device. It can support a maximum of 1 plant per planting cycle. The material is plastic and the size is 62 inch by 25 inch by 27 inch, and it connects through server via Wi-Fi. The second product is Grobo One. This product has a price of $1,999 or 64,800 baht. It consists of 5 sensors and it is not supported by the iOS or the Android device. It can support a maximum of 1 plant per planting cycle. The materials is plastic and the size is 48 inch by 14 inch by 14 inch, and it connects through server via Wi-Fi. The third product is Cedo. This product has a price of $2,004 or 64,700 baht. It consists of 10 sensors and it supports iOS and Android device. It can support a maximum of 1 plant per planting cycle. The materials is plastic and the size is 40 inch by 24.4 inch by 24.4 inch, and it connects through server via Wi-Fi. The last product is Cloudponics. This product has a price of $2,690 or 86,900 baht. It consists of 6 sensors and it supports iOS and Android device. It can support a maximum of 1 plant per planting cycle. The materials is plastic and the size is 69.75 inch by 30.75 inch by 29.5 inch, and it connects through server via Wi-Fi. Second step. In this step, we designed the prototype model by using Shaper 3D design application. And we designed the model to be as close as possible to the actual size. Now we will tell about our prototype component, including the ventilator, light source, air temperature and humidity sensor, and planting tanks humidifier, light source transformer, acidic liquid tank, alkaline liquid tank, fertilizer tank, water pump, electric wire junction, and holding tank. HMI, acidic alkaline and fertilizer pump, carbon filter, PLC, and water chiller. Last step is to build a demo. After we completed the design, we prepare the necessary equipment, then we build a real demo at our laboratory.
Material design. For our work, sometimes some equipment can't be bought, so we need to design and build it ourselves using 3D printer. Shape 3D design. First we have to design and shape 3D application before we build by using 3D printer. These are our design that we use in our project. The first one is servo motor platform. The second one is light sensor platform. The third one is stand for pH, water temperature, water level and DC sensors. The fourth one is light adjuster connector control by servo motor. The last one is case for Arduino board. 3D printer design. After we finished the design in Shape 3D, we created the 3D printer model. These are our 3D printing that we are already combined with our equipment. The first one is servo motor platform. The second one is light sensor platform. The third one is stand for pH, water temperature, water level and DC sensors. The fourth one is light adjuster connector control by servo motor. The last one is case for Arduino board.
Software design. Using PLC and HMI. PLC use for store and process the back-end software, and HMI use for store and display the front-end software. Software develop program. Back-end and front-end by using GP Pro X, ProFace for front-end, and Machine Expert Basic, Schneider Electric for back-end. Front-end. User interface structure. User will be able to access two modes, which is an auto mode and manual mode. When we open the HMI, first is the home page, next page is used for give a plant species to it, give a plant age, and select the mode. Auto mode. First page can select a kind of value. And this is the example of value. In this page is of graph and immediate value. Manual mode. Display always show immediate status and you can control all of value by yourself. Backend. Backend is very important system. It can generate values from sensors, send value to front-end and control all output. Results. Conclusion. Our autonomous in-house farming system was created to reduce the complexity of plantation process for those who are busy with their schedule and farmers who want to increase their productivity. The in-house farming system consisted of auto and manual mode, which user can choose between the two or swap between them. The front-end user interface was designed to be user-friendly and easy to use with everyone. The back-end was programmed by using GP Pro X and Schneider Electric Machine Expert Basic. Suggestion. In the future, we can develop our software to be compatible with more plants, and user can adjust the setting in auto mode where they can manually set their own plants.
Meet the team. Sirawachwat Charasan Makul. Priyapur Enchantra Kongrat. And Passan Patva Chuli Chot. Thank you for watching.